Okay, maybe I'll go from here itself. Uh, I'll be essentially covering reasoning-oriented retrieval today. And just before I get started, let me just quickly introduce myself. So I'm basically a final year PhD candidate with Professor Eugene Agichtein. And uh, before that, I worked in a company called Amelia.ai, where we built conversational AI assistants and conversational agents, you could call it in today's terms. And before that, I did my electrical engineering and biological sciences from BITS Pilani, India. So, what today we are going to look at is basically reasoning-oriented retrieval. And just to give a flavor of how, let's to do an analog of what could that be in a library setting. So, you basically go to a librarian, and you have some of your requirements for some book, and the librarian listens to you, goes to a first shelf, and gives you the book directly. So then you're not happy with the book. Then you ask the librarian with some other words. The librarian goes back, finds the second book, gives it to you back. So this is the more traditional search, analogous to how Google and Bing, we basically typed in one search, got results, and we did that back and forth. In reasoning-oriented search, ideally, you would think of, you would go to a librarian who is smart enough, who would think a little bit, who might compare different sources, take a look at different shelves, maybe talk to different librarians, and then come with a book which is probably more, that you might like it more. So essentially, we are trying to understand how reasoning-oriented search, this style of algorithms work. And in order to do that, we look at multiple directions. So first, we look at single-step retrieval, and then we'll move on to reasoning-oriented retrieval. And in order to understand reasoning-oriented retrieval, it is also important to understand how reasoning is in general used without retrieval in the non-RAG setting or the non-retrieval setting. That is a simple, you ask a query and the model returns an answer. So we'll try to understand reasoning there through three algorithms, at least two, that RLHF and GRPO. And then we'll try to use these algorithms for the retrieval counterparts while looking at iterative retrieval, specifically Toolformer and SearchR1. And if we have time, we'll also look at deep research agents as well. So, so let's get started. So in terms of how the literature treats these retrieval augmented generation tasks is through three popular tasks: short answer, multi-hop question answering, passage or document retrieval, and long answer, multi-hop question answering. So in the first task, essentially you have a user asking a query, you retrieve some documents, and finally using those documents, you try to come up with one short answer, which is your final answer. And that short answer is generally verifiable in the sense that it's easy to identify whether the answer is correct or not, because they will generally be like one or two words, something like factoid questions, like who is the president of, or who went here first. Uh, Passage and document retrieval essentially is the second step, intermediate step. I think this is what most of the course, IR course is about. Uh, the third one, long answer multi-hop QA, is essentially related to your deep research task, where you don't only retrieve documents, but after that you assimilate them and then generate a long summary out of it. Evaluating this is hard because you need to understand different facets of information, and it's not necessarily, you can't really do it with an exact match, right? So, and feel free to pause me at any moment and ask questions. Yeah. So short answer multi-hop QA, there are popular benchmarks like multi-hop QA, Wiki2Hop, and what we look further is BrowseComp and BrowseComp Plus as well. And most of these benchmarks generally have like a document source like Wikipedia. And some of the recent ones, as model capabilities are getting better, people have come up with benchmarks which directly talk with the internet, with the live web pages. So we'll take a look at that as well. And the evaluation of most of these tasks requires at least understanding two things. How good are retrieved documents, that is your retrieval effectiveness, and how good is the answer correctness. So retrieval effectiveness we see through metrics like NDCG, precision, recall, and we try to identify whether our gold documents, which are like top 6, 7 documents, how are they as compared to our predicted ranked documents. Um, for answer correctness, it is essentially an exact match or a F1 match, right? Uh, so there is traditionally, or like in the last couple of years, as we saw these single-step RAG approaches come up, and this is like the most basic form of retrieval augmented generation. So these are like this was made from popular via papers like Realm and RAG for knowledge-intensive tasks. And here, what the authors do is that they take a simple query, then they apply a BERT-like encoder to come up with a query vector, and then they perform they do the same with document vectors as well, and then they take the top k documents, and then whatever those top k documents, they are passed to a generator in order to generate a final answer. So now this is the inference pipeline, and for here, while training, the generator is also fine-tuned, as well as the query and the document embeddings are also fine-tuned. Now, one thing to understand here is that as soon as we start fine-tuning the query, the document encoder, that means our document index gets stale. So after a few epochs, then we can't really use that document encoder. So people generally do this at multiple episodes. So basically, after 10 or 20 epochs of training the generator, they go back and try to update the document indices. So there is a little bit of lag, but essentially, this is how a typical single-step RAG approach is trained. Now, you could see like this is still restricted to very simple queries, which require like a single step of retrieval. But sometimes we want to scale this to more complex retrieval tasks, and that is what we're going to look at today. So single step retrieval is insufficient because we have complex retrieval queries which may not necessarily match from a simple similarity search or a simple BM25 match. Because it may happen that our evidence is spread out across multiple documents which are completely unrelated, and we might need to generate multiple queries, gather these documents across these different sources, and then assimilate them. Right. So the whole point is to move to more dynamic way of doing this kind of retrieval. So before going to reasoning, let's look at multi-step RAG. So here, essentially, retrieval is performed multiple times. So what they do is this is just a prompting approach. They don't train it. We'll look at training approaches further. But essentially, what they do is that given a query, they first retrieve a set of passages. And once these passages are, then they are sent to the generator, which generates some set of reasoning tokens. And then these tokens itself are used to retrieve again. And so basically these generated tokens are then used to retrieve twice. So as compared to a single step retrieval, this multi-step prompted retrieval shows improvements across multiple benchmarks. And you could understand like how in different kinds of settings, such an approach would be really useful where our evidence is catered and we need to call when evidence is kind of collected as we move across multiple rounds of retrieval. So, so now the question is that the earlier one was a prompting based method. So can we essentially design trainable methods that can improve reasoning oriented RAG? And before that, we'll try to understand what reasoning is essentially. And in that, we'll first try to understand two main approaches. That is reinforcement learning from human feedback. And I think that is covered to a good extent by Professor Agichtein, right? So, but I'll go through it in depth. And then the second is the reinforcement learning from verifiable feedback, that is approaches like GRPO. So most of the lecture is dedicated to understanding these two, and then SearchR1 is basically an offset of this. So once GRPO is understood, then you can basically use that for any task, including SearchR1 as well. So yeah, so typically in any multi-stage training or any frontier model training, we generally have these three stages. That is a pre-training stage, an instruction fine-tuning stage, and a post-training stage. And the pre-training stage essentially collects all the web data which is there, and we have this large amount of terabytes and data which generally is not much looked at. Generally, it's either filtered or pre-processed automatically. Then we have instruction tuned, that is supervised fine tuning training, the training part of it, where essentially you give like query and response pairs. You give it an instruction and how to do that. So essentially you're kind of writing down the whole response. And then you use that to train the model, and you try to impart reasoning capabilities by basically writing down and telling the model, okay, like this is the thing. So we have essentially it's a supervised fine tuning task. The final one is the post training step. So, which is the focus of today's lecture. So, in the post training step, we'll either have reinforcement learning from human feedback, where humans would essentially be shown like two responses, one good and one better, or like two responses which we think are good enough. And the human would basically select one or the other. And we'll also discuss why we would want to do that. And the other alternative is RLVR, reinforcement learning from verifiable feedback, so or verifiable rewards. So here, essentially, the feedback does not come from humans, but they come from automated executions. So essentially, there might be, for instance, you're writing like a code generation RAG model, and your success criteria there is basically the code executes proper or not, or whether the code passes these test cases or not. So that is basically the verifiable rewards part of it. So you don't really need a human. You of course need a human to write that reward function, but essentially it's you don't need a lot of human annotated data. So we'll look at that. So the most famous paper, which basically made this kind of post-training or a reinforcement learning-based fine-tuning really popular, was OpenAI's Instruct GPT, and it had basically three stages. The first stage essentially collected the demonstration data or the instruction fine-tuned data, and then they trained a supervised fine-tuned model. So basically, this is converting a pre-trained model and convert into a supervised fine-tuned model. And then the supervised fine-tuned model was prompted to generate multiple answers. And then humans were told to, or our human annotators were told to rank these answers, the topmost to the best to the least. And then this data was used to train a reward model. And now this process essentially, now with the reward model, becomes dynamic. So with this reward model was then again used to further fine tune the instruction tune model of the first stage, and with an algorithm called PPO, which is what we'll look. So yeah, so before we understand like the importance of reasoning or the importance of algorithms like PPO, it is crucial to understand how previously such data or such instruction tuning data was really used. So most of traditional NLP tasks that you see, like especially before 2018, 2020, was a collection of these a lot of hand engineered tasks like common sense reasoning, dialogue generation, or question answering. And what people found that when you collect these tasks and when you train them together, you get improved performance. So there's a lot of benefit in this instruction fine tuning for sure. Then there was another effort after Instruct GPT where people tried to, a lot of researchers came together and did this, used Open Assistant. So basically, they wrote a lot of conversations. Um, then there was the interesting Stanford Alpaca approach as well, wherein a model was used to generate these responses and then basically generate these tasks, and that was used to fine tune our instruction tune our model. This was also one project, NL Augmenter, which essentially was like a collaborative project that I organized. So essentially, we wrote different Python functions. So every participant was asked to write a different Python function to convert one task date, like a data of a particular task, into its multiple representations. So you could think of like some form of data augmentation. So much of these basically uh, data sets required for instruction tuning required a lot of hand engineering. And if we look carefully at some of the examples as well, like a FLAN, which is the this first the collection of tasks. Um, for instance, like Ben, in speaking with Herman, he suggested that you look at the earnings on this, and there's a short answer, Blue Dog. But if you look at this question has like a long question, then some options, then another question, that is the second few short example, answers, then another question, and so on. So basically, humans had to write these few short examples in order to really come up with something really strong. And you also understand that, I mean, such form of surgical creation of data is really painstaking. Um, this is an open assistant example, a random example where the question is explain calculus to a primary school student, and the answer is a very long essay, and it's really tedious to write such long essays, and it can be really time consuming as well. So even like if we do like a small survey and ask like okay, which is the best coffee spot around Emory, and should I invite my friend there? And you would get, when you try to collect this from a bunch of even students who are motivated enough, you would get like very different answers from them. And it would be, so Caldi is the best coffee because they have the best lattes, but can be noisy. I don't drink coffee, so I'm not sure. Starbucks is lovely. No one will check what I wrote. So you could just basically get a lot of noise as well. You need to filter out some of those. For some of those, it might be, some of the responses might be like super ambiguous. So you're not sure whether you want to include them or not. So there are these problems. But look at GPT 5.3's response. And GPT 5.3's response is pretty amazing, right? It's pretty, you ask it like, what is the best coffee here? And then it gives a long response with pictures, with bullet points, and with a map here as well. So this would basically take like hours for a human to write, or at least minutes. So much of these NLP data sets, which we saw previously in the last decade, they varied a lot in different ways. They varied in length and style. Some had bullet points, some had images. Then there was implicit context. It's when people wrote down these examples as well, like people had different assumptions in mind. People had different cultural contexts as well in mind. So then the question is whether we wanted to add references or not. So at the end, do we support an answer with a reference or not? Then the scale, how much data do we collect? Should we collect like 100 MB of data, 1 GB of data, 1 TB of data, and so on? And all of this is essentially capabilities. There's the question of safety as well. Whether the responses are harmful or the responses are biased. That question is there as well. And models vary a lot in response length, right? So if you look at most of the popular data sets, you see like the response length is, sorry, even the input prompt is very different, like almost from 17 tokens to 291 tokens. And generally or loosely, the length of the input prompt signifies how complex a task is. So the completions are also varying, and there's kind of all possible combinations. But on the other hand, what do humans prefer? Humans generally prefer longer outputs. Humans prefer outputs which also have a list structure in them. So this is also like it's like a pain point, because now we need to take into consideration these different factors which essentially humans like, which are very different from the data sets that we created over all of these years, right? So uh, then there are other problems as well. For instance, there's this example from Open Assistant. Can you write a short introduction about the relevance of the term monopsony in economics? And there's a long answer, and at the end of the answer, there's also a reference. So when we give models such question response pairs, and this is quite a complex question, even in terms of the depth of knowledge required for that question, as well as the way the answer has been written. So when we try to teach such a model to learn such an answer, we are also implicitly teaching it to generate a reference in the end. And this can sometimes be problematic if the model does not have references, because then it will learn to hallucinate, and basically after whenever given a complex question, it might just be encouraged to generate some hallucinated tokens in the end, reference tokens. Yeah, a hallucinated reference. Yeah. So the question, so essentially, and there was a study done by John Schulman. He had a famous talk, and there were some other studies done essentially also, which told that the closer, or if you have a lot of these facts data in your pre-training, then you basically your subsequent stages of training are done better. So essentially, if you train on known facts, your model trains faster as compared to when you train on unknown facts. And the suggestion of most of these approaches or these results were essentially that we need some form of reinforcement learning. Like, it is a data set, yeah. Yeah. So yeah, that's the question. So because that is written by a group of researchers, and we do ideally, even if we do assume that's a let's say that's a standard response. But the question is also here, what I was trying to point out is that if the underlying model does not have strong capabilities, let's say it does not have some topics around this particular concept like monopsony, it might just hallucinate some reference. So even though this response is essentially a good and ideal response, but we might basically teach the model some wrong things. That's yeah. Researchers, yeah. Absolutely, that is a concern. That's a legitimate concern. Yeah, and so my argument for all of this is essentially that writing these responses is not a very optimal strategy, and that's why we'll move to reinforcement learning for that. Yep. Thanks for your questions. Yep. Yeah. So yeah, these are the main takeaways, that you may not want to fine tune on long tail knowledge, even. And in principle, RL style correctness feedback would help. So we need some form of reinforcement fine tuning. And knowledge storage and extraction in LMs is messy. Getting these data sets up is really a complex task. And it's very nuanced as well. So yeah, so now we come to the second part of the talk, which is reinforcement learning from human feedback, and this is the most interesting part of the talk, as well as the most interesting approaches of 2025 were essentially from this Instruct GPT paper. So we're going to come to the second section, which is training a reward model, like using getting these preferences to train a reward model, and then using that reward model for optimizing the policy using PPO. So supervised fine tuning essentially tried to had some reference distribution, input output examples, and we were trying to make our predicted policy y given x as similar as possible to this reference policy. And this was the pure generative modeling perspective, and also called imitation learning in reinforcement literature. The RLHF, on the other hand, what we are trying to do is we have our policy, and we are trying to maximize its expected reward under that policy for some reward function r y comma x. So we'll look at how we do that. Um, uh, yeah, so one of the other things that I think I should mention about is the cost required to do a lot of these annotations, and there's a lot of compute cost involved, and there's a lot of annotation cost involved. And that's where SFT data is really like our instruction tuned data and supervised fine tuned data is like super expensive. Uh, Apart from that, like this is also related to your questions is so there was this study done in which expert writers were told to write some summaries, and their writings were compared to model generated rewrites or model generated writes from scratch, and the expert writers themselves preferred the model generated um, writes. So there is this gap, and it's hard like to get like the ideal response. So even if it's researchers or even if it's like super domain experts, so and even RL is like reinforcement learning is also like uh, in terms of data generation, it's also crucial in terms of like how we look at search augmented or retrieval augmented systems. Because if we want to do some task, some RAG task, we are more concerned by the outcome than via the process as much. So we are not really concerned about the ideal way to search it, and the ideal way to search might be really hard to find. Um, but rather, we are just concerned whether our final answer is correct or not, and that basically this whole search RAG search pipeline essentially motivates us to look at things in a more reinforcement learning way, where we have like a sparse reward only at the end, and we don't really care about how the search process happens. So we ask a very complex question, and different agents or different people might go through different search approaches, but if they still come at the right answer, then we are still happy, right? So one is data collection. When Now we'll essentially look at collecting data to train the reward model. That is, train this second part of um, how do we collect data to train the reward model. So we saw that handwritten examples are a bit messy. So in a standard RLHF setup, we essentially have like a feedback, like a pairwise feedback setting, where a user is given a question and two AI responses, and the annotator has to select between rating response one is better, response two is better, or response one is slightly better, and so on. So essentially, in the most basic case, an annotator has to select which one, whether response one is better or response two is better. And I think you might have already seen this sometimes in ChatGPT as well. Like when you type, you are given two responses, and you have to select you like which one do you like more, right? So that is essentially collecting this pairwise feedback data to train this reward model. And collecting this data, generally annotators are given like guidelines, something like, and these are very long guidelines. So this is the guideline of Anthropic, where they decided to have like better preference according to helpfulness, harmlessness, and truthfulness. And they have like a very long documentation for annotators to follow. Yeah. This this is how RLHF data is collected, and there are problems with that as well. That it can be hard to collect really high quality verifiable annotators as well. People can still disagree on preferences, especially for very complex, controversial questions. For instance, it's hard to get them to check to correctness, and many annotators sometimes also use GPT-4 as well. So in many of the experiments, people have found that there's almost like a 90% correlation with some of the annotators with GPT-4. So you basically need to remove such annotators from your data gathering stage. Um, Yeah, so now we have the data. We have this pairwise data. So Now let's look at the method. So how do we adapt our model to basically make use of this pairwise data? And there are two approaches. One is the reinforcement learning approach called PPO, Proximal Policy Optimization, which we'll take a look at. And DPO, it's a supervised learning equivalent, but I think we might not have time for that. I might briefly talk about that as well. So yeah, so uh, the PPO approach is the proximal RLHF PPO approach is the equation is pretty simple. So what we are essentially maximizing is the rewards that our policy gets. And there is a second term, which is the KL divergence from our original policy, which is the supervised fine-tuned policy. So essentially, we have a pre-trained model, we have the supervised fine-tuned model, and now we are applying PPO on it. And so we are ensuring that when we train this model and create our RL policy, we don't go a lot far from our original policy, and that is controlled by the beta factor. So and the same, we do that for the pre-training data as well. So we ensure that the probability of our pre-training data is also a little bit is controlled so that we don't have any catastrophic forgetting. So this is how our policy is optimized in PPO setting. So is there any question regarding this equation particularly? Or do you want to take a look for a second at this equation? Proximal policy optimization. Right. So that is just the algorithm this that they call for in RLHF paper in the Instruct GPT paper. On a soup. So you could apply, people are doing that for both, for pre-trained model as well as supervised fine-tuned model. When this paper came out, they did that on the supervised fine-tuned model. Yeah. Yeah. So, yeah. So so that's in the next equation. Yeah. I'll tell you. Yeah. Yeah. Okay. So, so essentially, this is the part where the human feedback is incorporated. So this is essentially the Bradley-Terry preference model, and so this might have been covered initially for generally pairwise preferences. So what this essentially says is that there is some hypothetical reward model of the world, which basically tells us what is the reward of a particular response. So every response that is generated has some reward, but we don't see that reward. Instead, what we see is like we tell these annotators, and these annotators give us some preferences. So we see these preferences. So the preferences are observed. Our reward model is not really observed. What we essentially observe is this pairwise feedback, which is like a sigmoid applied over the difference between the chosen response and the dispreferred response. So essentially, this loss equation is important. So this helps us basically train our reward model, right?
Or you're saying instead of you're rewarding like so the human is selecting which answer they prefer, and then you reward the weight of the reward is based on which answer they prefer.
So we'll basically the loss on the reward model. So we are optimizing the reward model's parameters here, theta, with how much it can basically give a high reward. So if a model essentially gives a high reward for a response, we want to ensure like so okay. So essentially we take these preference annotations between a a good response and a bad response, and we use that, and then we subtract, we take the difference and use that to update our parameters of our reward model. So if our reward model gives like a higher value for um, our the negative response, then as compared to the positive response, then accordingly we have a higher loss. So that's how it's reflected. Essentially, those pairwise preferences are reflected. So accordingly, the model updates its it will update its parameter. So this is a supervised trained model. So the reward model is still a supervised model, but how the reward model is used, it's used in through PPO for training the policy model. That is the reinforcement learning part. Yeah. So this is PPO at a very conceptual and a high level. So this is your reinforce gradient equation. So what are we interested in? So we are interested to maximize our expected rewards. And in order to maximize our expected rewards, we are taking a gradient. And when we take a gradient with respect to the policy parameters, and when we are taking a gradient with respect to the policy parameters, this is equivalent to basically taking a gradient of the policy parameters itself. Sorry. So we want to optimize our reward, and the equation for taking the gradient of the expectation of this reward is equivalent to taking the gradient of our policies parameters. So this is the general reinforced equation. This is not PPO. So this is uh, this is the general reinforcement equation, and then comes TRPO, Trust Region Policy Optimization. So essentially, one problem with this is that it uses the reward function. What TRPO does is TRPO replaces this reward function with something called the advantage. And the advantage is essentially a variance reduced version of the reward. So that is one change. The other change is this factor. So this factor is basically an off to on policy correction. So essentially what this says is that when our policy is generating these rollouts and then we are rewarding them, so we want to do them in batches. And hence we want to allow our policy to go a little bit stale. And if we allow our policy to go a little bit stale, we could only do that via a correction. So here essentially pi theta is our online policy, the one which is exactly getting trained. Pi theta old is something which is like a few epochs away. Then there is another term which basically keeps our old policy and our new policy under some, like the KL divergence is there is a limit put to the KL divergence so that it does not deviate way a lot from the original policy. Then comes PPO. So PPO essentially takes this KL divergence term and it and basically plugs in and converts it into this clipped fashion essentially. So what this says is that our original term, our off to on policy correction with the advantage should lie between 1 minus epsilon to 1 plus epsilon of our original term. So we are basically we are not allowing gradient updates to be very large. That is like essentially gradient clipping. So the derivation for this, it's not there in this slide, but essentially it's in any reinforced lecture we'll find that derivation. So just the reinforced equation, and finally we come to the PPO equation. So most of the approaches of like papers of Instruct GPT, even like further down the line, DeepSeek, as well as like Kimi, they will essentially have this two terms. One is optimizing the rewards, and the other is the KL divergence or the clipping term to basically control how far your updates go. So. Yeah, so there is DPO as well, which I will just quickly skip. but I think I'll just quickly mention as well. So essentially, DPO is the supervised fine-tuning version of RLHF, and what the authors did was the authors like looked at this preference data. They said that okay, instead of training an intermediate reward model, let's try to directly use this to train the LM policy. Um, but here, then this becomes like a supervised fine-tuning problem. But there are other problems of this as well, which we'll take a look further. So, um, yeah. So now we come to the more interesting part of like this lecture called reinforcement learning from verifiable rewards. And here the algorithm of GRPO is not very different from PPO. It's and you'll see like most of the today's or like 2025's successful papers in especially in math reasoning and logical reasoning and a lot of verifiable tasks of like DeepSeek as well as Kimi 1.5 and Quen. They all used GRPO or some variant of it. So why do we essentially need another RL algorithm? So why not PPO and why not DPO? So one problem with PPO is that it requires an advantage computation, which essentially requires a value model. That means apart from the policy, we need to have like a separate GPU for just training the value model itself. And um, DPO essentially DPO is offline and the data is not inherently pairwise. Uh, we yeah so yeah so this is the main equation, which is GRPO, group relative policy optimization. So this is not very different from PPO. Essentially, we have one term, which is the the clipped advantage function that we saw in PPO, and we have the KL divergence term. Now, what is the difference here is that previously the advantage was computed using a value model. And we have some rewards, and then we basically train a value model in order to compute those advantages. So here GRPO gets rid of that value model. What they instead do is that they introduce this concept of group. So the advantage of a response I, for instance, is the reward for the response I minus the average of the rewards for all the responses in that particular group divided by the standard deviation of that group. And now, what is a group? A group is essentially different types of responses for a similar set of prompts, like essentially the same equation. Either you could have a single prompt with multiple generated rollouts or multiple responses, and that would constitute a group. Or you could have like very extremely similar questions, and that which are essentially have the same answer, and then you have responses to them. But the group is not like a batch. A batch is different. A batch will have two different examples of different types. So they'll have different questions and different responses. Here, kind of, you can assume the question is the same. So the query is the same, and for each query, we're essentially sampling um, capital G responses or rollouts, OI. And we are essentially taking them and then computing this advantage estimate. So this advantage estimate is kind of like the z-score of the reward. So this was the PPO, just for reference, and it had this clipped advantage function. So that is essentially what we see here. Only now we have a summation over all the group rollouts. So yeah, any questions here? Okay. Okay. So uh, there are a couple of flaws of GRPO which is an interesting line of study for like your projects as well, or if you want to do further work in this. And one is training instability. There's a lot of severe reward hacking as well. So uh, because once we are essentially giving rewards at the final step, the model basically could generate something completely else and still get the reward. Um, and there is inefficiency in multi-step or multi-objective environments. So when we have a single reward function which essentially computes is rewards the rollouts, we are not giving some more fine-grained information. So it is, for instance, if we uh, give like a score of 1 for a correct math format plus a score of 1 for getting the correct math answer, the model just the policy might give the uh, same might generate like a bad format correct answer versus a correct format bad answer, but they both might have the same reward. So there are problems like this, but I think we'll move on to like how do we incorporate search in this setting. So yeah, so now we understood like essentially what GRPO is in the non-RAG setting. We'll try to apply this in the RAG setting. And we saw this earlier, the multi-step RAG approach, which was a prompting-based approach, where we essentially had like we had a sequence of calls being made to the retriever without really having any sort of autonomy to it, or trying to change any of its original behaviors. So um, then there was also another line of work called Toolformer, which was basically a supervised fine-tuning approach by trying to predict search tokens. So what they did was, so here the essentially the task is that we are given a query and we need to make external calls in order to generate our final answer. So the Toolformer folks essentially created data. They created in an interesting way, but this was a supervised fine-tuning approach, and the approach was essentially to um, take a regular data set, sample API calls, and then filter these calls according to whether when we insert these calls into a regular text, that is a regular example. So a regular example does not have any search calls, but after putting these explicit search tokens here, does the loss of the subsequent tokens decrease? If the loss of the subsequent tokens decreases, then this is kind of like a needed search call, is what they conclude. And this is how they create such annotated calls data. So essentially, you take a regular example and then insert these kind of like fake search calls. And so when the during inference time, when the model is generating tokens one by one, and it will reach here. So as soon as it generates like an open bracket, you kind of know that okay, it's possibly a search query. So you let it complete till it generates a closed bracket, and whatever inside of this, you make a search call, and then take that information and insert it here. So that is what essentially the Toolformer approach did. But now this requires a lot of collection of training data as well. And so why not use some form of reinforcement learning, things that we learned in GRPO, and use that for training such an approach itself, such a Toolformer based approach, but instead of the heavy manual writing or even like automated inserting these fake search calls. So yeah, so the reinforcement learning approach is essentially SearchR1. The and SearchR1 is not really super different. So it is essentially like GRPO plus a retriever. Um, to be like use that in like to say that in a single sentence. So what they do is they have an initial prompt which basically tells the model, okay, like if you must conduct reasoning inside think and close think first every time you get new information. And after reasoning, you find some, if you lack some knowledge, you can call a search engine by the search tokens, and it will return the top search results between the open information and closed information. So you can search as many times as you want, and if you find no external knowledge, then you can generate these close answer tokens. So essentially, during inference time, we pass this prompt. During training time as well, we pass this prompt, and we hope that the model will basically generate these intermediate search queries, and whatever the search results are, that would be put in the information token, and then we'll stop as soon as we see the answer tokens. So this is what SearchR1 did, right? Um, just to also quickly have just to quickly give a brief overview. We have an input query, a policy model, a search engine, and a maximum action budget, which essentially controls the number of tool calls or the number of search calls that the model makes. And then we initialize our current LLM rollout sequence, which will basically be the generated tokens up till now. And then we keep sampling tokens. And if we find either a close search or a close answer, then we break. And if our tokens essentially have a search query, then we execute that search query, get the search results, and then insert those search results in the information token, and uh, then continue generating until we see like a open answer slash answer. So that is what the SearchR1 process is, right? So essentially, so here, if you see like the rewards are given by the final step, whether the correct answer is there or not. So, and that's how GRPO is trained. Um, one thing that is an interesting part that they did was loss masking for retrieved tokens. So essentially, when the policy model retrieves some external tokens, these tokens will be very out of distribution from the original policy because it could come anywhere from the internet. Uh, so they found that when you insert these tokens and take a loss masking over all these tokens, you find like the loss goes very high. So for the retrieved tokens, they essentially masked those tokens and then computed loss over all of the other tokens, like the answer token or the query calling or the search token. Yeah.
So the search R1. So
This.
that's kind of like the the tool former, right? The tool former also kind of research.
Yeah. So, but the thing is, for Toolformer, you are actually collecting these trajectories first artificially. So think of like if you have a question like um, a complex question which requires multiple retrieval calls. So you essentially find some data on the web which goes through all these trajectories, insert fake search calls there, and use that as supervised fine-tuning data. That is what Toolformer did. In SearchR1, we are essentially only rewarding the final step, which is the reward. We are saying we'll give you a reward of 1 if the final answer that you generate is correct, or we'll give you a reward of 0 if the final answer is wrong. So, and in the prompt, we basically directed that you have these capabilities, you have these tools that you can go and search and come back and insert these search retrieve tokens into your context.
So you can so, like
We don't manually insert, no.
it's deciding if reasoning itself.
Yes, yeah,
If they choose to use the tool to just reward the final answer. Right?
correct. Yeah. We still need to train it. So one thing regarding reinforcement learning or these post-training approaches is that it generally improves the behaviors which are already existing in the model. So, like for instance, this prompt, right? So, if the model's original policies that it generated, original rollouts that it generated, they didn't have these search and information tokens really well generated, then uh, the model might the rewards of those will always be 0, and the model might not get any feedback to train a better policy. So that's why sometimes post training is also most often used to kind of amplify certain behaviors rather than kind of like create new behaviors from scratch. So. So like SearchR1, there were other approaches as well, which basically tried to expand this and do this sort of reinforcement learning based search training. So like R1 Searcher used like a two-stage curriculum. So in the first stage, they used a retrieval reward plus a format reward. And here the retrieval reward was essentially if the reasoning tokens have at least one retrieval call, then you get a reward of 1. And if the format of the reasoning tokens is appropriate, then you get a reward of 1. So, and only in the search stage, they then remove the retrieval reward, and here they just give the reward to the final answer. So essentially, it's like in the first stage, you're teaching the model to perform retrieval, and in the second stage, you're teaching the model to do that retrieval in order to get the correct answer. So, and apart from RAG, people have used like RL and GRPO based approaches for re-ranking as well, which is the second stage retrieval, which is essentially rank R1. So here, the system is given a prompt wherein given a user query, which of the following documents are most relevant. So a first stage retriever like BM25 is used to retrieve some top 20 documents, and then these documents are fed to a model like Quen or any of the fine-tuned or reasoning models. And then then this is trained as a RL policy. And whenever the policy rollouts generate the correct document ID, that is given a positive reward, a reward of 1. So that's how the model is trained to policy trained to do re-ranking as well. So. Yeah. The other task we till now we saw most of these tasks were short answer QA tasks, wherein the final answer was kind of verifiable. Here we look at long form generation tasks where the final answer is generally long and not verifiable. Um, so here we are not just interested in whether the final answer matches or not, which is an exact match, but we have a long answer which can have various ways it can be correct. And we are more interested then in the quality of the answer, that is how relevant the final answer is to the original query, and how well grounded or how less hallucinatory it is, or how faithful the answer is to the retrieved documents. So people have kind of uh, extended the search R1 approach, wherein for long form RAG tasks, wherein they've changed the reward function from just a static reward to like a reward model itself. So now you just don't do an exact match. You don't have a function. You have a reward model. So and that reward model will basically will generate a score, and that would be used and back propagated to fine tune your policy. Yeah, then we have like 6 minutes, so I'll quickly cover this as well. So this is also an interesting. Sorry, this is I was recording some of my lectures, so yeah, I should maybe delete this. Yeah. So essentially, this is the most interesting part of I would say today, 2026, 2025 is deep research agents, and I'm sure most of you might have used this somewhere, like as a in Gemini or ChatGPT. You? Have you? No. So essentially, okay. So we'll cover it, but I think you should use it today. Uh, I think I've been using that since I think like about since when it came. I think almost a year probably maybe. Yeah. So. So yeah, so what is deep research? So deep research in terms of a task, it's the ability to generate a long summary using information that is hard to find. So let's say something like writing a survey paper, for instance. You could go on and you need to go through different sources and try to extract information from those different sources and then also assimilate them in order to write a long form report. So that is what deep research is. And to create a good deep research system, you need like the model or the system needs different skills. One is query reformulation or query formulation. That is whether it's how it's interacting with those search systems, how to create those queries autonomously. The second is strategic perseverance. That is what to orchestrate, like how many queries to create, which query to fire first, which query to fire second, and so on. And the ability to assemble these fragmented clues. And there are different benchmarks. For instance, we created this benchmark called ConQRet, which was for controversial questions and long form argumentation. So here we are giving like a controversial query and we have different sources of evidence, and using them, we need to generate a long form answer. Then there is this like interesting data set from BrowseComp, and you see like the queries are have like a very complex nature, like between 1990 and 94 inclusive. What teams played in a soccer match with a Brazilian referee, had four yellow cards, two for each team, where and so on and so on. So um, these queries are complex in the way that they require to create like appropriate queries as well as extract evidence from different sources. So um, so when they created BrowseComp, they essentially when also the tasks the main aim was to basically test the ability of models to browse the internet and answer a short question. And when they asked the humans to solve, essentially humans took about like 3 to 4 hours to solve a single question. And while the tasks which humans, the queries which humans could not solve, humans gave up like after 2 hours. So these are pretty challenging questions. So so now, how do models perform on BrowseCom? Zero shot performance. So these figures are from 2025. So definitely numbers would have changed now. But at that time, at least zero shot performance was very poor, and all most of the standalone without any exposure to data. Open AI O1, which used some sort of reasoning, had basically some 10% accuracy. Deep Research one, which OpenAI did not release how they trained it. That system that achieved a good accuracy of 51 as compared to the others. Um, One of the other also interesting tasks that I like quickly mention about is the asymmetry of verification. So if you decide to create like a data set or a benchmark, or you want to write a paper on it, in today's day, you also need to think of like whether these tasks would be automated completely by many of these reasoning models or these or the latest models. So one way to kind of it's not a hack, but it's like a strategy that people often employ is this asymmetry of verification, wherein you just need to ensure that your answer is correct. If your answer is correct, then it's you can still come up with a good benchmark or a task. So essentially, like some tasks are easier to verify than to solve. So if a model generates some answers, we should be able to at least verify them, even if we can't provide like a solid way to solve that task. So um, yeah, so then there is BrowseComp Plus, which was essentially a local version of BrowseComp. So these authors basically instead of doing search on the internet, they do search on a local index. I will skip this as well, but essentially this is another benchmark. So um, yeah, so I'll keep 2 minutes for asking questions. If you have any questions. or you want to discuss something. The subsequent slides which I had were for agentic design patterns and for deep research agents. So I will just, so there have been like multiple approaches where people attempted to design these multi-agent systems. So basically, try to write, essentially, it was either trying to write prompts in a different way and trying to build a deep research system, or trying to train it using an algorithm like GRPO to build the same. So, and of course, this is for the search part. For the long form generation, people use some form of judge as well. But yeah, I think I'll stop now. Let's see.